And this is what the final solver will look like. And even if it might seem something really complicated, you can see that inside each wrangle there is not that much code. And I decided to make it this way because basically each node will take care of something inside the setup. And despite this means that you have to carry some attributes over the different nodes, it will make this setup very easy to debug, because if you have a problem with something, you just need to deactivate everything else and it will be much clearer for debugging purpose. And you can argue with me that you can always do this in a single wrangle and use some parameters to act as a global multiplier for each effect. I mean, if we are talking about improvements, there's really no end to it. So this is what is working for me right now. Okay, so drop down a subsolver and dive inside. As we said, we are going to build this thing step by step. And the first thing we want to see is actually these points to move, so we can have some visual feedback right away. So drop down a point wrangle. We will call this move. This will take care of the point movement. And here we want to act on the moving group, even if right now all the points are in the moving group. And in here, first, let's create a float variable. We will call this speed. So we have a global multiplier for the movement. So chf speed. And now, if the current frame is greater than 1, because I don't want to this solver to cook on the first frame, then we're going to update the point position. So at p plus or equal the speed we created multiplied by the direction vector we already have. And if we set, let's say, the speed to 0.1, we should already have some movements here, and we do. Now, before modifying the direction of the branch, we actually want to compute some trail, because as it is right now, it will be very hard to judge the movement of the branch. So we want to drop down another point wrangle here after the move. Let's make it red. We will call this trail. And if I go outside for a second, I want to unplug the last point and set the scatter to 1. It will be easier to explain. Basically, in the trail node, we want to add a point each 5 frame, let's say. So this time, beside the frame greater than 1, we also want to add the condition to the frame modulus than 5 to be equal 1. So it will trigger every 5 frame. And inside, actually the quickest way to generate a trail will be just to add a point. So int pt to create an integer variable, add point function, geometry 0 on the current position. And now we just want to remove the point we just created from the moving group, otherwise also the trail will move. So geometry 0, the group is moving, the pt is the point we want to take, and we want to remove it from the group, so 0, and the mode is set. And we want this node, of course, to act only on the moving group. So if we go outside and we go forward, we do have something like this. The problem by generating a trail like this is that in the end, we actually want to connect this point with some lines. So if we drop down an add node and choose polygon by group, it may seem correct now, but if we transform just, let's say, the point number 0, which is always at the end because it's the one that is moving, you can see that we have an extra line here because the lines are generated with the point order in this case. So until here is correct, but you will always have this extra line connecting the last point to the first one. So here, either you delete the last point of the branches after you work with the solver, but I prefer to do it in a different way. Basically, we want to swap this situation. When the point trail will be generated, the original point will stop, and the one that will move will be the point that we're generating here in this wrangle. So basically this set point group, which is acting to the new point, will be set to 1. So we are adding that point to the group, and we want to copy and paste this line. And for the current point number at ptnum, we want to set this to 0. But now, if we play it, they will stop after the first point, because the downside of doing like this is that the new point doesn't have any direction or up vector. So we need to add a few lines of code to transfer all the attributes we want from the current point to the new point. And for now, we just have direction and up vector, so let's just transfer those. So set point attribute, geometry 0, we want to transfer the direction to the new point, and the value will be the current attribute, so be at dir, and the mode will be set. Copy and paste this line and do the same for the up vector. So up will be at up. And this should have restored the movement. And as you can see now, if we go outside, we should, why I did delete the connection, I don't know. You can see that now we have the correct order and the point number 0 is right at the beginning. But now if we restore the scatter points to 12, even without adding the last, and replay it, we do have this. And this is happening because the add node is connecting all the points, so it can tell apart the different branches. So before the solver, where we initialize all the attributes, we also want to compute some id value. So after the toVector, let's create a string attribute. We will call this id, and it will be equal to the string branch plus the current point number, which we need to convert to string from integer. So I to A, the current ptnum. And now, if we go here and check the ID, we do have a name for each branch. So basically, on the add node, we don't want to connect all the points, we want to connect by attribute, and the attribute is ID. And that's still not enough, because we need to transfer also the ID now for the trail points. So back here, let's copy this line again and transfer the ID, which we take from the s@id attribute, and we are still not using the mass, but we will use, so might as well transfer that too. So set point attribute mass, and that is a float attribute, so f@mass. And hopefully now we should have the correct polyline, and we do. Now let me template the trunk and re-enable the noise. Basically, inside the solver, regarding the rotation, we will do several operations in a stacked manner. And the first thing I want to do is to change the direction as they grow, because I like the tangent fashion compared to the trunk for the first part. Then the first operation we want to do is basically to flat all the branches on the ZX plane. So they will start tangent, but then they will flat out and go completely horizontal. Then on top of that, we will add other operation, but the first time will be that. So basically flatten out all the branches. And to do that, and to do also the further operation, we basically need to compute some age value for the branch. We need to know how old that branch is to modulate all the operation we're going to do. And whenever you need to compute some age value, you also need some reference to the birth frame. So in the init wrangle, I want to set a new integer attribute. We'll call this birth, and will represent the birth frame. So for this initial point outside the solver, we can set it as 0. Now go back inside the solver and let's drop down another point wrangle, and this time we want to place it right after the input. Let's make it blue and let's call this age. Here we will compute the age of the branch. So for this wrangle, we also want to act only on the moving group. There's no need to compute continuously the age for all the trail points. And in here, let's create a float variable, and the age will be equal to the current frame minus the birth attribute. So this is to say the initial point, this will start at 0, but let's say a point is born on frame 50, so 50 minus 50, because we will register this birth attribute also on the new point that we're going to generate, so we will have a correct computing of the age value. And now to compute a normalized age from 0 to 1, we can set the attribute f at age is equal to age divided, let's say, 250, basically 10 seconds of life. And here we should already have the age computed. And I don't know if we can see the animated one on the spreadsheet. Let's create a visualizer for it. And this can be a marker text. And we should see the age growing, as you can see, from 0 to 1. The only thing is that now all the branch have the same life. Maybe we want to randomize this a little bit. So after the float variable, we can add an integer random factor, and we want to use the random function over the ptnum, and let's multiply it by, let's say, 11, using also the int function. So basically we are generating a random number from 0 to 1, multiplying by 11, so 0 to 11, and we are converting to integer, which will seal the last value, so we will end up with from 0 to 10 only integer. And we can add this to the overall life, so 250 plus rand. What's happening? Oh, the semicolon. And now we have small randomize between the life of each branch. Now, what we're going to do with this age in this first operation, basically, if we take this point as an example, right now is growing toward its initial direction. Basically, what we're going to do for each point is to extrapolate its direction in a flattened way. So let's say something like this, flattened on the y-axis. And as the age of the branch grows, we want to interpolate between these two directions. So basically, the point will start like this, and as they grow, they will flatten on the horizontal axis, something like this. So here, let me also reconnect the final points, one at the end. And inside the solver, let's drop down another point wrangle after the age. All the tweak on the direction, we need to do it before the moving wrangle, of course. So this will be our flat operation, make it green. Here we want to act only on the moving group like the other one, and we don't want the age row just as we computed, so let's create another variable, float age, and we will feed the original age to a ramp, so age ramp, and we want to take the age. And now let me copy the line for the trail because it will be the same condition. So if frame greater than 1 and modulus of 5 is equal to 1, then we want to change this direction. So first off, we need two vectors. One to store the original direction, so we call this init dir. We will take the original direction, and then another one which will be the flat direction, so flat dir. Basically we want to just use the x and z component of the original dir and set the y to 0, so set init dir dot x, we are taking the first component, 0 for the y, and init dir dot z for the third component. We also want to normalize this just to be on the safe side. And now we just want to create a final direction, so vector dir. We want to use the lerp function between the initial direction, so init dir, the flat direction, and our bias will be the age with the ramp, so not rage, age. And finally, we bind it updating the direction vector. So if we don't touch the ramp, we should see the branch flattening over the course of their age, something like this. But we want something way more flattened in the just the beginning of the branch, so something like this. And let's also display the base to see our proportion. We are definitely too fast with the speed of the growing, so on the move, let's half it to something like 0.05. So this makes more sense in terms of proportion. And this calculation is not entirely correct because we need to also normalize the final vector. So now we should have, let me hide and re-enable the line, something like this. And if we template this line, basically we have the original direction just at the beginning of the growing. We can tweak this later, but I believe we will leave it as it is. So now we need to add further deformation on these branches because we don't want them to be horizontal, but now that we're moving in a flat space, we can add some orientation based on the mass and the height of the trunk. But before doing further modification to the direction, we want to create another wrangle to fix the up vector because right now, if we display the up and the direction, if we take, let's say, this point as an example, you can see that we are updating the direction vector, but not the up one. The up vector is not maintaining its perpendicularity with the direction vector. And instead of fixing this up vector each time we tweak the direction, we want to make another point wrangle. And let's copy the flat one, actually. We will call this fix up, so we can use the condition inside. And we want to put this at the end. Here we will put all the others modification to the direction, but before moving the point, we will fix the up vector. So in here, what we want to do is we already have the group. We can delete this age ramp because we don't need this. And let's delete also this line and delete also everything inside. So inside here, first we will retrieve the original direction. So be at dir and also the up. So be at up. So the way we want to fix this up vector is basically by creating a new vector that we will call projection that will be equal to the dot product multiplied by the direction vector. What this means is that, let's say we have this first point with the direction, which is the green one, and the up vector, which is correctly perpendicular to the first one. When we modify the direction without modifying the up, we end up with something like this. This is not more perpendicular. And the dot product can basically tell us how much two vectors are not perpendicular to each other. And the dot product basically will give us 0 when two vectors are perpendicular to each other, -1 when the two vectors are opposite, and 1 when the two vectors are identical to each other. So basically it's a range going from -1 to 1 that can tell us, hey, these vectors are not perpendicular by this value. And we need to make a vector with this. So we want to multiply it by the direction. So basically this projection vector is just a vector that is telling this point that is this vector away from being perpendicular to the direction vector. So in practice, let's create a vector variable called proj. And as we said, the dot product between the up vector and the direction vector multiplied by the direction. So basically now we know that the up vector of point 32 is this vector away to be perpendicular to the direction vector, which means we just need to update the up vector, and we want to use the normalize function, and we want to subtract from the original up this new vector we created. This will realign the up vector. So let's just bind it to this, and we need to give it a unique name. So let's call it new up, and this will be equal to new up. So if we play it now, it's not working, or it is. Let's see, let's recache everything on 0. Sometimes the solver goes a little bit crazy when you're watching from inside. So let's see. Yeah, the up vector now is updating itself. So now we can tweak the rotation further and stay in peace that all our vectors are updating correctly.